Good morning and good afternoon to all the fellow attendees across the country. My name is Niranjan Sitapuri, and today we are going to talk about multi-scale modeling of spray coating of perovskite quantum dots, especially for application in solar cells. And I'll explain why this is an important step in a shift towards renewable energy in the future. This is the presentation outline we are going to follow today, and my first job is to provide you with some background and motivation for this work. The first question we need to ask is, what are perovskite quantum dots? These are nothing but perovskite structure semiconducting nanocrystals of around a size of around 5 to 10 nanometers. So they're very small in size, and they come in the wide family of compounds. Generally, they come as cesium lead bromide, which we are going to talk about in this work. Now we are interested in these perovskite quantum dots because of their amazing optoelectronic properties. For example, they have very high luminous nature. They have a very high quantum efficiency. That means a very less amount of incident lights get wasted. You can also control the wavelength of these emissions based on their size. So it's very a nice system that we can control. As a result of these amazing properties, quantum dots find applications in next generation displays and solar cells. The vibrant colors and energy efficient nature is used in display technologies. For perovskite solar cells, because of the high quantum efficiency, when incident light or incident photons are used on these functional layers, very less of the photons get wasted, and you will have high exciton formation, which means you will have a better efficient solar cell. Also, that means you will require less material utilization, making it cheaper to produce perovskite solar cells. On that note, the perovskite solar cell market is expected to increase by 30% annually in the coming years. Also, the solar cell efficiency has reached a record 22%. Given the nascent stage of this technology, it's a commendable fact. Furthermore, the quantum dots can be made using solution processing using continuous crystallizers at even low temperatures, which saves a lot of energy as compared to the heat intensive Chokalski process for silicon solar cells. And that's why there is a huge impetus for manufacturing of perovskite quantum dots and perovskite solar cells. That being said, there are certain challenges in commercializing this technology, and one of the key challenges is the batch processing nature. So today, the thin films used in perovskite solar cells are made using something called a spin coating, which is nothing but the quantum dot solution is dropped on a revolving substrate as shown here, and then you make a thin film out of it, which can then be put in an oven, cured, and used. However, there is a lot of batch to batch variation. The low material utilization is pretty low. Also, it is very difficult to control the thin film porosity and roughness in this case. And that's why we need a better alternative, which is more continuous and which can be at a higher production level. And one ways to do it is using spray coating. In spray coating, you have a nozzle which has your quantum dot solution, and it sprays the quantum dot solution on a substrate of a certain size. So you can control the size of the substrate. And this process can be continuous, where the substrate is coming and going, and you're spraying your quantum dot solution. The quantum dots get deposited, and you have your thin film, which then can be used in a solar cell. Furthermore, you can control the temperature of the spray, the velocity of the spray, the position of your substrate, and that's why it gives you a much better control over your thin film. However, uh, if you want to scale it up and if you want this to for industrial production, it is very essential to do accurate modeling of the spray coating process. Thus, when you look deeper into the spray coating process, you will realize that the phenomena is happening at two different scales. At the macroscopic scale, when you are trying to spray a liquid droplet, the distribution of the droplets needs transport modeling. Also, the solvent which is there in the particle, which is there in the solution, needs to be evaporated so that the quantum dots can actually deposit on this silicon dioxide substrate and form the film, which will require a thermal modeling. However, on the other hand, at the microscopic scale, on the substrate itself, the quantum dot particles are going to have some interactions. They are going to aggregate, and this aggregation itself needs to be modeled. Thus, for the complete understanding of the spray coating process, we need accurate and simultaneous modeling of both the macroscopic and the microscopic scale, and that's why we are going to present a multi-scale model in this work. And now I will show you the modeling methodology that we have used. So let's first look at the macroscopic scale. So if imagine you have this substrate which is maintained at a temperature Ts, and you have this droplet which is spray coated on it of a certain diameter, and as this droplet impinges on the substrate surface, it's going to create a liquid splat. So we need to know what is the size of this liquid splat, what is the thickness, and this can be calculated from transport phenomena using some of the dimensionless numbers we have, and you can see the reference below. And this dimensionalization helps into scaling up this model. So if you want to scale it up for a higher production, we can, it is very easy to do it. Once we know the size of the drop, we know that the substrate is heated at a temperature Ts and the drop which are impinging are at room temperature. So they're going to start to heat up and the solvent it starts to evaporate. So we can model this process by writing a heat balance across the liquid splat. Also, we realize that because these drops are very fine, they are atomized. The temperature dependence is there for evaporation, as well as there is a size dependence. So as the liquid drops keeps on evaporating, they become smaller and smaller, which leads to having a difficult evaporation. And this is a well documented phenomena. Then as we start to look at the molecular scale, we realize that one of the interactions available is going to be the Brownian motion. So the quantum dot particles, which are shown here in a droplet, can show Brownian motion and they can randomly move around in the solution. And this can be modeled using a Gaussian noise as shown here. And then we can decompose the Gaussian noise in an X and Y direction. Secondly, these quantum dots will also show van der Waal interactions between each other, and this interaction can be approximated with a Hamaker constant approximation, and the force between these particles follows an inverse square law as it is shown below, and you can find the actual details in the references as well. Also, we will have some dipole interactions because quantum dots have the ABX3 structure and it's asymmetric in nature, which creates electron clouds to get distorted and leads to dipole interactions. The dipole interactions can be modeled using an inverse square law as well, which is given below, and we can find the dipole moments from literature. Finally, since the quantum dots have some ligands on its surface, when two quantum dots come close together, they can show steric repulsion, as it is shown schematically here, and we can approximate this steric repulsion using the polymer brush theory, which gives us the repulsive force as shown here. Finally, the sum total of all the forces can be calculated using the Newton's law of motion for each particle, and then we can predict how each quantum dot particle is going to aggregate with each other, how it's going to move around. And this way of calculating forces or simulating a molecular system is called the discrete element method, which we have used in this work. Now we can look at some simulation results. In the beginning, we have to initialize the model, and in this case, we have considered that the substrate temperature is around 100 degrees because the boiling point of solvent is 110 degrees. We assume that the nozzle velocity is around 100 mm per second and the diameter of nozzle is 0.3 mm. And this is taken from one of the examples in the literature. Also, each liquid particle or each liquid droplet will have millions of quantum dot particles, but then you cannot simulate all of them because of the computational expense. Thus, we assume that each of the drops will have 10,000 particles, which are representative of the aggregation dynamics. Firstly, let's look at the evaporation rate of the droplet or the splat. So initially, when the splat is fully formed as a higher radius, the evaporation rate is high, and as the splat radius becomes smaller and smaller, it becomes difficult for the evaporation to occur and the evaporation rate drops. And this is because, as I had mentioned previously, that not only is evaporation controlled by the concentration difference and the temperature, but also by the size of the splat. And it's a very well documented phenomena that happens when you are dealing with evaporation of very small droplets. Furthermore, as the droplet is evaporating, which is shown by the black boundary here, that the droplet is evaporating, the particles inside the droplet are mobile and they're aggregating as we speak. Also, these are divided into two categories, like the mobile particles and the immobile particles. So basically, the quantum dot particles which are within the liquid drop can still move around and aggregate. But once the droplet has dried, the quantum dot particles become stationary and they essentially get deposited, which is how spray coating deposition works. And these are shown by the red particles. As a result of particle aggregation and the simultaneous evaporation of the droplets, we get something called as the coffering effect, which is very characteristic of spray coating systems. So basically the particle starts to aggregate, and as the droplet starts to evaporate, the particles become deposited at a boundary. And you will realize that as you can see time proceeds, they form this ring formation, which is called a coffee ring formation, which is very frequently seen in very different spray coating processes, and is an essential feature of this model that we can predict it close to reality. Furthermore, if we zoom into this aggregation process, you will realize that Brownian motion brings the particles close to each other. Then the attractive forces between these particles take over and they can form an aggregate. There is another aggregate which is also now getting attracted to form an aggregate 2. And this is exactly how the aggregation process is happening at the microscopic scale. Further, to quantify this process, we've plotted the histograms of different size clusters with time. What I mean by different size clusters is basically different quantum dot particles can aggregate together to form clusters which are small shaped, medium shaped, intermediate shaped, and large shaped. So initially you will find that most of the clusters are small and medium shaped or size. And then as time proceeds, you will see that the medium shaped clusters grow, they aggregate, and eventually you will see that most of the small clusters and medium clusters aggregate to form these large clusters which are of sizes greater than 100. We can better understand this if we plot a bar graph of the cluster sizes and their evolution. So initially we have a lot of small and medium clusters. Then as time proceeds, you will start to see formation of these large clusters which has more than 100 particles with the yellow bar here. And as time proceeds, the number of clusters also start to decrease because more and more small clusters are now turning together to form larger clusters. And eventually, as the droplet evaporates, the cluster size distribution kind of saturates to a certain value. This brings us towards the climax of this work, and I'll explain you why this work is important when we are trying to design better thin films for perovskite solar cells. So far, I explained why spray coating can be used as a good alternative for large-scale production of perovskite solar cells. However, the modeling requires a multi-scale modeling approach. For example, we saw that the evaporation of the quantum dot solution is size dependent and needs to be taken into consideration. Also, at the molecular level, the molecular interactions between the different quantum dot particles cause them to aggregate and actually form the thin film. However, this also leads to the coffering effect, which is characteristics of an uneven deposition of quantum dot particles. However, now that we know the problem at hand, we can use a better control strategy to try to control this uneven deposition of particles. And this leads us to very new exciting future works, which I'll talk about. For example, now that we know how one liquid drop is can be simulated, we can extrapolate this process for the entire film, and then we can predict the porosity and film roughness of the entire quantum dot thin film, which will affect the perovskite solar cell performance to a great value. Also, we plan to validate our cluster formation model, which gives a quantitative idea of the aggregation process using some experimental data. And finally, knowing all this information, we can actually design model-based controllers to achieve a uniform film deposition, which will in turn directly affect the perovskite solar cell performance. I would like to say thank you to all of you attending, and I'll be happy to answer any questions.